Welcome to our introductory tutorial, What Governs Animal Cell Cultures in Bioreactors? Through the Bioprocess Engineering online tutorial series, you gain expertise in the principles of bioprocess engineering and their applications to enzymatic bioconversions, microbial fermentations, and cell cultures bioprocesses. For more details, please visit us at bioprocessengineeringonline.com. Animal or mammalian cells are increasingly employed in the pharmaceutical industry for the production of a wide range of biopharmaceuticals, including recombinant glycosylated proteins, most notably monoclonal antibodies, viruses used in the development of vaccines and as vectors for gene therapy, living cells themselves applied directly as therapeutic products in the field of cellular therapies. For biopharmaceutical production, animal cells are cultivated in a diverse range of bioreactor systems, spanning small-scale formats, such as roller bottles and spinner flasks, to large-scale industrial stirred tank bioreactors. When animal cells are cultured in bioreactors with nutrient media, they consume key substrates such as glucose, glutamine, and oxygen. In batch processes, glucose and glutamine concentrations typically decline steadily over time as they are taken up by the cells. Dissolved oxygen concentration, however, often shows a more complex trajectory. It initially decreases, reaches a minimum, and may subsequently rise again due to changes in cellular metabolism and oxygen demand. Concurrently, the viable cell density increases, reaches a maximum, and subsequently declines, while the concentration of non-viable or dead cells correspondingly increases. As a consequence of their metabolism, animal cells release various byproducts, most notably lactate, ammonia, and carbon dioxide, and in engineered lines may also secrete recombinant proteins of interest. In batch cultures, lactate and ammonia concentrations typically increase steadily over time. Dissolved CO2 concentration often follows a nonlinear trend, rising initially, reaching a maximum, and then declining as cellular activity changes. For recombinant protein-producing cells, product concentration generally increases over time, although secretion may begin only after a lag phase associated with growth and metabolic adaptation. When scaling up bioreactor cultures from laboratory to industrial scale, the main challenge is to reproduce laboratory-scale culture dynamics as closely as possible, achieving comparable cell densities and recombinant protein productivities at larger volumes. In this tutorial, we will address two key questions. What are the fundamental biochemical and physical phenomena that govern cell culture dynamics in bioreactors? How do these fundamental phenomena change during scale-up? In bioreactors, the time-dependent variations in the concentrations of culture components are governed by three fundamental phenomena: cellular reaction, mass transfer, and fluid flow. The primary driver of these concentration changes is cellular metabolism, specifically the rates at which cells consume substrates, grow, and produce metabolites and recombinant proteins. In addition, physical phenomena play a critical role in shaping culture dynamics. Mass transfer, particularly the rates at which oxygen and carbon dioxide are exchanged between the gas phase and the culture medium, and fluid flow, the circulation and mixing of liquid elements within the bioreactor. In cell culture bioreactors, the dominant factor governing process dynamics is the cellular reaction. The overall duration of the culture, along with the final cell density and product concentration, is largely determined by cellular activities, namely the rates of growth and death, nutrient uptake, and metabolite or product formation. These activities depend strongly on the cell line employed and on the mode of growth, whether in suspension or attached to solid supports such as microcarriers. Cellular specific rates are dependent on many environmental parameters that generally change during cultures. First, the concentrations of the substrates or nutrients in the culture medium. There are the concentrations of glucose, glutamine, other amino acids, peptides, growth factors, dissolved oxygen. Second, the concentrations of the excreted metabolites, mainly the concentrations of lactate, ammonia, and possibly of dissolved CO2. Third, physicochemical variables, such as the medium temperature, pH, and osmolarity. Cells may also be affected by the physical stresses induced by the medium stirring and by the bursting of air bubbles. The most influential kinetic characteristics of cells include growth rate limitation by substrate availability, particularly glucose, glutamine, and oxygen. Growth rate inhibition by accumulated metabolites, notably lactate and ammonia. Acceleration of cell death rate due to toxic byproducts, especially lactate and ammonia. The kinetic characteristics of a given cell line determine the temporal evolution of specific cellular rates during culture. Following the initial lag phase, cultures typically exhibit a progressive decline in cell growth, substrate uptake, and metabolite production rates, largely driven by nutrient depletion, oxygen limitations, and the accumulation of inhibitory byproducts. A corresponding increase in the cell death rate associated with the accumulation of lactate and ammonia. How are cellular reaction governing phenomena scaled up? Among the different phenomena influencing cell culture, cellular activities are typically the most directly transposable from small to large scale. This is because cells respond primarily to their immediate microenvironment, the local concentrations of nutrients, metabolites, and dissolved gases, rather than to the total culture volume. As a consequence, similar cell growth and metabolic kinetics can often be reproduced across scales, provided that comparable microenvironmental conditions are maintained. However, certain scale-dependent effects can introduce variability. For example, increased shear stress at larger scales may lead to higher cell death rates, particularly for shear-sensitive cell lines. Differences in the physiological state of the inoculum between scales can also influence the length of the initial lag phase, affecting early culture dynamics. The kinetic laws that describe cellular rates as functions of environmental conditions are presented in the tutorial, Animal Cell Kinetics in Bioreactors. Mass transfer is the second fundamental phenomenon governing cell culture dynamics, primarily controlling bioreactor aeration. Cell culture bioreactors are continuously aerated to supply oxygen, essential for cellular metabolism, and to remove carbon dioxide, a metabolic byproduct that can inhibit growth. This constant gas exchange is necessary because of the low solubility of oxygen and carbon dioxide in aqueous culture media. The supply of oxygen in the fermenter occurs in three stages. First, oxygen is introduced into the fermenter through the inlet air system. Next, a portion of the oxygen transfers from the air phase into the liquid medium. Finally, the cells present in the medium consume the dissolved oxygen for metabolic activities. Similarly, the removal of carbon dioxide follows a sequential process. The cells in the medium produce carbon dioxide as a metabolic byproduct. The carbon dioxide then transfers from the liquid medium into the air phase. Lastly, the outgoing airflow carries the carbon dioxide out of the fermenter, effectively stripping it from the system. Oxygen transfer from the gas phase into the liquid medium occurs through three consecutive steps. Transport to the interface. Oxygen moves from the bulk gas phase to the gas-liquid interface by diffusion and convection. Dissolution at the interface. Oxygen molecules cross the interface and dissolve into the thin liquid layer adjacent to the surface. Transport into the bulk liquid. Dissolved oxygen diffuses and is convected from the surface layer into the bulk culture medium. The rate-limiting step is typically the transport of oxygen across the liquid boundary layer into the bulk phase. This occurs through both molecular diffusion and convective mixing, with the latter strongly dependent on local fluid velocities near the interface. The oxygen transfer capacity of a bioreactor is primarily determined by the gas-liquid interfacial area available within the system. This includes the surface of the culture medium exposed to the headspace, the surface area of dispersed air bubbles, which generally provides the dominant contribution. The bubble surface area depends on the airflow rate supplied to the culture, the type of sparger, which strongly influences bubble size distribution. In addition, oxygen transfer capacity is affected by the efficiency of oxygen transport within the liquid phase, which depends on convection and mixing intensity, that is, the fluid velocities and turbulence within the medium. The dissolved oxygen concentration is determined by the balance between the two consecutive oxygen transfer from the air to the liquid phase and oxygen consumption or demand by cells. During a batch culture, the oxygen consumption rate initially rises during the cell growth phase, reaches a maximum, and further declines. To maintain the balance between oxygen transfer and consumption, the dissolved oxygen concentration decreases during the rapid growth phase, reaching its minimum when oxygen consumption peaks. It then gradually increases as the culture oxygen demand decreases. Similarly, carbon dioxide transfer from the liquid medium to the gas phase occurs through three consecutive steps. Transport from the bulk liquid, dissolved CO2 moves by diffusion and convection from the bulk culture medium toward the liquid layer at the surface. Desorption at the interface, CO2 molecules cross the interface and desorb into the gas phase. Transport into the bulk gas phase, CO2 disperses away from the interface into the surrounding airflow. The rate-limiting step is the transport of CO2 through the liquid boundary layer, that is from the bulk liquid to the gas-liquid interface. This transfer occurs via both molecular diffusion and convective mixing, with convection strongly influenced by fluid velocities near the interface. The dissolved CO2 concentration is determined by the balance between the two consecutive CO2 production by cells and CO2 transfer from the liquid phase to the air. During a batch culture, the cellular CO2 production rate increases during the exponential growth phase, reaches a maximum, and subsequently declines as growth slows and metabolic activity decreases. As a result, the dissolved CO2 concentration rises during the rapid growth phase, peaks when CO2 production is at its maximum, and then gradually declines. How are the governing mass transfer phenomena scaled up in bioreactors? Because hydrodynamics and bubble circulation patterns differ across scales, oxygen and carbon dioxide transfers are not directly transposable from laboratory to industrial bioreactors. As a result, both the mass transfer capacities and the resulting dissolved oxygen and CO2 concentration profiles can vary significantly during scale-up. Moreover, scaling up aeration may introduce additional challenges, such as foaming and cell damage from bubbles rupture at the overhead air interface. In practice, the objective of scale-up is not to reproduce the exact time course of gas concentrations, but rather to ensure that dissolved gas levels remain within physiologically acceptable ranges. Oxygen must be maintained above critical levels to sustain metabolism and viability. Carbon dioxide must be prevented from accumulating to excessively high concentrations that can inhibit growth and reduce productivity. The third fundamental phenomenon influencing cell culture dynamics is the flow of the medium within the bioreactor. The flow field is defined by the distribution of fluid velocities inside the vessel. It depends on impeller geometry, shaping whether circulation is predominantly radial or axial. Agitation intensity, power input, set by the stirring rate, which governs overall mixing strength. Medium rheology, particularly viscosity, which can change during culture as cell density and metabolite concentrations increase. The intensity and distribution of fluid velocities exert multiple effects on bioreactor performance. First, they determine the mixing efficiency within the vessel. Effective mixing ensures a homogeneous distribution of cells, nutrients, dissolved gases throughout the culture. In microcarrier-based processes, adequate flow also maintains a uniform suspension and distribution of microcarriers within the medium. Second, fluid velocities within the culture medium directly affect convection-driven mass transfer efficiency. Higher fluid motion enhances the rates of oxygen transfer into and carbon dioxide transfer out of the liquid phase. Consequently, the intensity of mixing influences the dissolved oxygen and carbon dioxide concentration profiles during culture. At higher stirring rates, one typically observes a smaller decline in dissolved oxygen and a reduced accumulation of dissolved CO2. The fluid velocity patterns within a bioreactor can also exert a direct influence on cellular activity. Velocity gradients between adjacent fluid elements generate shear forces, which can damage shear-sensitive animal cells. In addition, cells may be exposed to turbulent eddies in the stirred medium. When the eddy size approaches or falls below the cell diameter, significant shear stresses can be imposed. Excessive shear stress can reduce cell viability, alter cellular metabolism, and ultimately decrease productivity. To mitigate these effects, several strategies can be employed. Addition of shear protectants or stabilized cell membranes. Optimized impeller design and agitation rates to balance mixing efficiency with minimal shear. How are the governing fluid flow phenomena scaled up in bioreactors? Fluid flow phenomena represent one of the most challenging aspects of bioreactor scale-up. Unlike cellular reactions, which are primarily local processes, hydrodynamics scale non-linearly with reactor size, leading to significant changes in radial and axial velocity patterns. The objective of scale-up is not to replicate small-scale hydrodynamics exactly, but rather to achieve a balance. Sufficient flow intensity to ensure medium homogeneity and effective oxygen and carbon dioxide transfer. Moderate hydrodynamic stress, avoiding excessive shear that could damage sensitive cells. In practice, the aim is to establish a hydrodynamic environment in which cells experience acceptable ranges of mixing, aeration, and shear stress, thereby supporting growth and productivity comparable to those observed at smaller scale. In summary, in this tutorial you learned that in bioreactors, the time-dependent variations in culture component concentrations are governed by three fundamental phenomena: cellular reaction, mass transfer, and fluid flow. The primary driver of culture dynamics is the cellular reaction, characterized by the rates at which cells consume substrates, grow, and produce metabolites or recombinant proteins. In addition, physical phenomena critically shape the culture environment: mass transfer, governing the exchange of oxygen and carbon dioxide between the gas phase and the culture medium; fluid flow, determining medium circulation, mixing efficiency, the intensity of convective mass transfer, and the shear stresses experienced by cells. Together, these biochemical and physical processes dictate the dynamic behavior of nutrients, biomass, and metabolites throughout culture. They also establish the fundamental limits of achievable performance, including maximum cell density and final product concentration. The fundamental phenomena of cellular reactions, mass transfer, and fluid flow provide the basis for knowledge-driven simulation models in bioprocess engineering. Such models allow the prediction of dynamic variations in nutrients, cells, and metabolites across different bioreactor operating modes. They are powerful tools that support the digital scale-up, control, and optimization of animal cell culture processes. The development and application of cell bioreactor simulation models will be explored in greater detail in an upcoming tutorial. If interested, you can gain a deeper insight in animal cells kinetics by enrolling to the online courses Introduction to Animal Cell Culture Technology and Engineering, and Digital Scale-Up and Optimization of Animal Cell Culture Bioreactors. For further information, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com. We hope you found value in this introductory tutorial on bioprocesses. Your feedback is important to us, so please share your comments with us. Explore our website for more information about our comprehensive online courses in bioprocess engineering, and be sure to subscribe to our Bioprocess Engineering online channel for upcoming tutorials. Thank you for watching.